Hi class, how are you today? I'm confident that that's great. The learning target for today is to be able to compute confidence intervals for mu when sigma is unknown. Scale, you're a 3 if you can compute confidence intervals for mu when sigma is unknown. 2, you can find critical values using degrees of freedom and confidence levels. 1, you can calculate degrees of freedom if given the sample size, and 0, you cannot calculate degrees of freedom if given the sample size. Let's get started. Section 7.2, Estimating mu when sigma is unknown. And there's a dot again for some reason. Focus points for this lesson: learn about degrees of freedom and students' t-distributions, find critical values using degrees of freedom and confidence levels, and compute confidence intervals for mu when sigma is unknown. What does this information tell you? In order to use the normal distribution to find confidence intervals for a population mean mu, we need to know the value of sigma, the population standard deviation. However, much of the time when mu is unknown, sigma is unknown as well. In such cases, we use the sample standard deviation S to approximate sigma. When we use S to approximate sigma, the sampling distribution for x bar follows a new distribution called a student's t-distribution. Student's t-distributions. Student's t-distributions were discovered in 1908 by W.S. Gossett. He was employed as a statistician by Guinness Brewing Company, a company that discouraged publication of research by its employees. As a result, Gossett published his research under the pseudonym Student. Gossett was the first to recognize the importance of developing statistical methods for obtaining reliable information from samples of populations with unknown sigma. Gossett used the variable t when he introduced the distribution in 1908. To this day, and in his honor, it is still called a student's t-distribution. It might be more fitting to call this distribution Gossett's t-distribution. However, in the literature of mathematical statistics, it is known as a student's t-distribution. The variable t is defined as follows. A student's t-distribution depends on sample size n. Have you heard me say student's t-distribution enough? Student's t-distribution. Assume that x has a normal distribution with mean mu for samples of size n with sample mean x bar and sample standard deviation s, the t variable. So t equals x bar minus mu over s divided by the square root of n. So very similar to what we dealt with, but with s instead of sigma. Has a student's t-distribution with degrees of freedom df equals n minus 1. If many random samples of size n are drawn, then we get many t-values from equation 12. These t-values can be organized into a frequency table and a histogram can be drawn, thereby giving us an idea of the shape of the t-distribution for a given n. Fortunately, all this work is not necessary because mathematical theorems can be used to obtain a formula for the t-distribution. However, it is important to observe that these theorems say that the shape of the t-distribution depends only on n, provided the basic variable x has a normal distribution. So, when we use a t-distribution, we will assume that the x distribution is normal. Table 6 of Appendix 2, also in the front of your book, around where the z-scores are, gives values of the variable t corresponding to what we call the number of degrees of freedom, abbreviated df. For the methods used in this section, the number of degrees of freedom is given by the formula df equals n minus 1, where df stands for the degrees of freedom and n is the sample size. For each choice for degrees of freedom gives a different t-distribution. The graph of a t-distribution is always symmetrical about its mean, which, as for the z-distribution, is 0. The main observable difference between a t-distribution and the standard normal z-distribution is that a t-distribution has somewhat thicker tails. Figure 7.5 below shows a standard normal z-distribution and student's t-distribution with degrees freedom 3 and degrees freedom 5. So notice that the normal distribution is much skinnier and much lower than the t-distributions of 5 and 3. Those are wider, and the tails are much thicker. There's a lot more space underneath the tails. Properties of a student's t-distribution. The distribution is symmetric about the mean 0. The distribution depends on the degrees of freedom, which is n-1 for mu confidence intervals. The distribution is bell-shaped, but has thicker tails than the standard normal distribution. As the degrees of freedom increase, the t-distribution approaches the standard normal distribution, and the area under the entire curve is 1, just like with all the other distributions. Using table sits to find critical values for confidence intervals. Table sits of Appendix 2 gives various t-values for different degrees of freedom df. We will use this table to find critical values t sub c for a c confidence level. In other words, we want to find t sub c such that an area equal to c under the t-distribution for a given number of degrees of freedom falls between negative t sub c and t sub c. In the language of probability, we want to find t sub c such that the probability that t is between those two is c. This probability corresponds to the shaded area in this figure. Table sits of Appendix 2 has been arranged so that c is one of the column headings and the degrees of freedom df are the row headings. To find t sub c for any specific c, we find the column headed by that c value and read down until we reach the row headed by the appropriate number of degrees of freedom. You'll notice two other column headings, one-tail area and two-tail area. We will use these later, but for the time being, just ignore them. Convention for using a student's t-distribution table. If the degrees of freedom you need are not available, use the closest degrees of freedom in the table that is smaller. This procedure results in a critical value t sub c that is more conservative in the sense that it is larger. The resulting confidence interval will be longer and have a probability that is slightly higher than c. Use Table 7.3 excerpt from Table 6 of Appendix 2 to find the critical value t sub c for a 0.99 confidence level for a t-distribution with sample size n equals 5. So, they told you ignore these two parts. We want degrees of freedom, which is 5 minus 1, which is 4. And then we want a 99% confidence level, so we look for 0.99. And we drop down, and here it is, 4.604. First, we find the column with C heading 0.990. Next, we compute the number of degrees of freedom, n-1, which is 4. We read the column under the heading, C equals 0.99, until we reach the row headed by 4. The entry is 4.604. Therefore, T sub 0.99 is 4.604. Confidence intervals for mu when sigma is unknown. In section 7.1, we found bounds plus or minus e on the margin of error for a C confidence level. Using the same basic approach, we arrive at the conclusion that E equals T sub C times S over the square root of n is the maximal margin of error for a C confidence level when sigma is unknown, i.e., the absolute value of x minus mu is less than E with probability C. The analog of equation 1 is the probability that x bar minus mu is between negative t sub c times s over the square root of n and positive t sub c times s over the square root of n equals c. Procedure. How to find a confidence interval for mu when sigma is unknown. Requirements. Let x be a random variable appropriate to your application. Obtain a simple random variable of size n of x values from which you compute the sample mean x bar and the sample standard deviation s. If you can assume that x has a normal distribution or simply a mound shape, symmetric distribution, then any sample size n will work. If you cannot assume this, then use a sample size of n is greater than or equal to 30. Confidence interval for mu when sigma is unknown. Mu is between x bar minus e and x bar plus e, where x bar is the sample mean of a simple random sample, e equals t sub c times s over the square root of n. C is the confidence level, which is between 0 and 1, and T sub c is the critical value for the confidence level C and degrees of freedom n minus 1. Suppose an archaeologist discovers 7 fossil skeletons from a previously unknown species of miniature horse. Reconstructions of the skeletons of these 7 miniature horses show the shoulder heights in centimeters to be these. For these sample data, the mean is x bar is about 46.14, and the sample standard deviation s is about 1.19. Let mu be the mean shoulder height in centimeters for this entire species of miniature horse, and assume that the population of shoulder heights is approximately normal. Find a 99% confidence interval for mu, the mean shoulder height of the entire population of such horses. We assume that the shoulder heights of the reconstructed skeletons form a random sample of shoulder heights for all the miniature horses of the unknown species. The X distribution is assumed to be approximately normal. Since sigma is unknown, it is appropriate to use a student's t-distribution and sample information to compute a confidence interval for mu. In this case, n is 7, so the degrees of freedom is 6. For C is 0.999. Table 6 of Appendix 2 gives t sub 0.99 is 3.707 for 6 degrees of freedom. The sample standard deviation is s equals 1.19. So, the margin of error, we plug in t sub c, s, and n. We get 3.707 times 1.19 divided by the square root of 7, which comes out to be about 1.67. The 99% confidence interval is mu is between x minus e and x plus e, so 46.14 minus 1.67, and 46.14 plus 1.67, so mu is between 44.5 and 47.8. The archaeologist can be 99% confident that the interval from 44.5 centimeters to 47.8 centimeters is an interval that contains the population mean mu for shoulder height of this species of miniature horse. On a calculator, if you press stat, then tests, then t-interval, then stats, then calculate, it will help you get the answer. Summary. Confidence intervals for the mean. Assume you have a random sample of size n from an X distribution and that you have computed x bar and s. A confidence interval for mu is, again, mu is between x bar minus e and x bar plus e, where e is the margin of error. How do you find e? It depends on how much you know about the X distribution. Situation 1, most common. You don't know the population standard deviation sigma. In this situation, you use the t-distribution with the margin of error we've been using, where degrees of freedom are n minus 1. Although a t-distribution can be used in many situations, you need to observe some guidelines. If n is less than 30, X should have a distribution that is mound-shaped and approximately symmetric. It's even better if the X distribution is normal. If n is 30 or more, the central limit theorem implies that these restrictions can be relaxed. Situation 2. Almost never happens! You actually know the population value of sigma. In addition, you know that X has a normal distribution. If you don't know that the X distribution is normal, then your sample size n must be 30 or larger. In this situation, you use the standard normal z distribution with margin of error that we learned last time. So, which distribution should you use for x bar? Example the problem statement. If sigma is known, use the margin of error with z sub c times sigma over the square root of n. If sigma is unknown, use the student's t distribution with margin of error t sub c times s over the square root of n, with degrees of freedom n minus 1. Now time for the sponge. Suppose x has a mound-shaped distribution, a random sample size 16 has a sample mean 10 and sample standard deviation 2. A, find the critical value t for a 0.90 confidence level. B, find a 90% confidence interval for mu. And B again? Or C, explain the meaning of the confidence interval you computed. That's it for the lesson. Once again, please make sure to take notes in the entire lesson. Go back, rank yourself, take a picture of everything, submit it all to Google Classroom, and have a good night.